Hello friends, welcome to IMS GATE Academy. I am Sourav Upadhyay, your mechanical engineering mentor, and I hope that your preparation is going good and almost the examination is here. And in the last ditch attempt to do something good in terms of revision, I am here with the session of heat transfer. My dear friends, I am expecting that all of you are aware of the important concepts, are aware of the important questions, have all the concepts in the back of your mind. Still, I will try that through this session, all those concepts would be revised in a very less time, that is, whatever is the length of the session. My dear friends, the subject is heat transfer, and you know that last year in a set a question of the total questions of around 8 marks was asked in a session. So we simply cannot make we cannot take a pre-notion in our mind, we cannot carry a notion in our mind that a particular subject will carry a particular amount of marks. We should be open minded. That being said, it can HT can come for around 5 to 7 marks on an average. My dear friends, what are the important chapters in heat transfer? Conduction, convection, radiation, heat exchangers. And the session will be started through the first chapter, and that is conduction. Conduction, very easily I have told conduction, but you know that so many concepts are there in conduction, starting from the generalized heat conduction equation, then the sub cases, and then the case of heat generation is there, plane slab is there, cylinder is there, spheres is there, lumped analysis is there, that is the unsteady case, and then fins is there. So many cases are there, and without wasting any time, my dear friends, let us straight away go in the session, right? So let me start with the session, my dear friends. My dear friends, conduction is what we are discussing. Conduction is what we are discussing. So what is the governing law of conduction? Can anyone tell me? The governing law of conduction is Fourier's law, and that is this is the Fourier's law of conduction. Fourier's law. So my dear friends, this is what? This is for 1D, one dimensional, and this is for steady state. So my dear friends, theoretical stuffs I will try not to tell much, because those are the things that are already in your notebooks. Mainly I will be concerned with the expression part, the concept part, right? My dear friends, before proceeding further, before proceeding to the generalized case of heat transfer, that is the 3D equation, let me tell you a good thing. Let me tell you a very something from maths. My dear friends, what is this that I have written? This is the Taylor's expansion of the function x fx around point x equal to a. Now suppose I have considered x minus a is equal to h and x equal to a plus h. So what happens? In place of x I am able to put f of a minus a plus h, and therefore fa plus h f dash a plus h square by 2 factorial f double dash a, and so on. Now you will be wondering that why I am telling this concept in the beginning of HT. My dear friends, ignoring higher terms, I can write what? Now my dear friends, focus on this part. focus on this part. And now my dear friends, if you compare this, I can write this. My dear friends, the next part, that is the three-dimensional heat conduction equation that I am going to tell you. In that we study this concept that, let's say here at this phase the heat is Qx, and after a distance of dx it is Qx plus dx. So it is required to find what will be Q of x plus dx in terms of Qx, and we write this equation. So from where it has come? It has come from the Taylor series only. That is why I told you the concept of Taylor's expansion, right? And if this is clear, my dear friends, in the entire conduction it has been used like anything. So many times it has been used, right? So I hope you are not missing this. So my dear friends, yes, and now it's the time of 3D heat conduction equation in Cartesian coordinates. My dear friends, Cartesian coordinates, that is x, y and z, Cartesian coordinates, right? What happens, my dear friends? What happens? A 3D element is taken. No, I am not going to derive, but it's important to give you an idea about from where it is coming. A 3D element is taken. This is dx, this is dy, this is dz, anything you can take as per your wish. Now my dear friends, this is what? Qx. So you are required to find the heat at Qx plus dx. This is Qy, so here it will be Qy plus dy, and sorry, this is Qy, this will be Qz, this will be Qz, so it is Qz plus dz, and this is Qy, so it will be Qy, so here it will be Qy plus dy. Fine. There is heat generation also. In this element, what is heat generation? This is heat generated in elemental volume, or this volume, in this elemental volume. Then what happens? Then energy conservation is being applied in this small element, considering that heat is taking place from all the three phases. Heat generation is being taking place, and we are considering the unsteady state also. That means it is storing, the element is storing heat in it. So considering all those things, if you apply the energy conservation equation, my dear friends, what do we get? We get equation something like this. Yes or no? Yes or no? See, my dear friend, these are the things which you should remember always. This is the thing that we get, right? For arriving this equation, I have only considered that the material is homogeneous, that is density is equal to constant. Now here if you apply the second assumption, that material is isotropic, so what happens? Kx is equal to ky is equal to kz is equal to k, that means property is same in all directions. And the third assumption is that k is independent of temperature. So what happens, that k you can take outside of this integration. All in all, if I have to apply all these three assumptions, take k is outside, so I will be reaching over here del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square plus q generation by k, and this is rho c by k. Yes or no? I'll be reaching over here. My dear friends, you know that alpha is k by rho c, thermal diffusivity. Yes or no? Thermal diffusivity unit is what? Meter square per second. So you can also write in this way, del 2 t by del x square plus del 2 t by del y square plus del 2 t by del z square plus q generation by k is equal to 1 by alpha. Yes or no? My dear friends, this much you should always remember. This much you should always remember, that how the equation is being started, right? Now over here we can do so many things with this equation. For example, like if I consider what? Tell me. If I consider no heat generation. So what happens? Q gen equal to 0. In this equation you will put Q gen equal to 0, and this means this part and this part will be there. Fine. Second, if I tell you steady state heat transfer, so what will you do? You will simply put del T by del of with respect to T is equal to 0. So only the LHS remains and RHS becomes 0. And finally, if I tell that steady state with no heat generation, so what will happen? You will put this equal to 0, this equal to 0, and what we are left with only this thing, the Laplace equation. Yes or no? Yes or no? Over here, if I tell you that only one dimensional equation is taking place, so you will only write del 2 t by del x square equal to 0. Yes or no? So my dear friends, what I am saying is that you should remember that how the equation is coming. At least this much you should remember, so that even if they ask you questions from the middle of something, you will be able to answer it. Fine. So I think you have got everything related to this. So without wasting any time, let me come to the case of plane slab, my dear friends. Let me come to the case of plane slab. See, it is what? It is steady. What do we say? Steady, one dimensional steady state heat transfer with no heat generation. My dear friends, so many things you need not remember. When you remember the assumptions, automatically this will come. You will be getting the how to make equations. So see, steady is there, so del T is 0, no heat generation, that means Q gen is 0, 1D dimensional, that means Y and Z will be 0. So automatically you know that you have to write del 2 T by del x square is equal to 0. My dear friends, we have to obtain T with respect to x. See my dear friends, I need to find out that this is the plane slab, the length is L, it is T1, here it is T2. I want to see the variation over here. Fine, cross sectional area is A, this is x equal to 0, this is x equal to L. I want to know how it is varying, yes or no? So if you solve this, my dear friends, it is what? T equal to C1x plus C2. So immediately I know that it is varying linearly. So C1 and C2, if I have to find out, I have to apply what? Boundary conditions. So at x equal to 0, temperature is T1. At x equal to L, temperature is T2. Yes or no? And if you apply all these things, my dear friends, you will get you will get this temperature profile which is varying linearly. And now my dear friends, if I have to find out heat transfer, so what is the slope? The slope is what? T2 minus T1 by L. Yes or no? This is the slope and this minus sign is also there. So you have to compensate. So this becomes your heat transfer equation. Fine. You know all these things. So this is the heat transfer equation for a plain slab. But you should know that what assumptions I have taken, and that I have already discussed few minutes back. My dear friends, the unit will be what? The unit will be watt. What is the unit of K? The unit of K is watt per meter Kelvin. This is meter square, and you can say that is temperature by, that means Kelvin by meter. Fine. My dear friends, what is the concept of thermal resistance? What is the concept of thermal resistance? Suppose this is a electrical circuit, current is flowing and this resistance is R. So what will you write? V1 minus V2 is equal to IR, del V is equal to I into R. Similarly, suppose this is T1, this is T2 and this is heat flowing. So there must be some resistance, and that we call as thermal resistance. So if you just compare these two, and now I am bringing you what is the heat transfer equation in plain slab. So it is what? Ka T1 minus T2 by L. So what you can write? K Q is equal to what you can write? Q is equal to L by Ka is equal to del T. So just compare, del T is equal to Q into L by K. So just compare, my dear friends, just compare. This is RTH. So what will be RTH? RTH will be L by K. If someone asks you what is the unit, unit is what? See, del T by Q. Del T by Q means what? Degree centigrade by watt or Kelvin by watt. So just remember that what is the heat, thermal conduction resistance in case of slab? It is L by Ka. L by Ka. Fine. So this much you have to remember. My dear friends, the same concept you can extend it to convection also. How? By Newton's law of cooling, I can say that. By Newton's law of cooling, what I can say? By Newton's law of cooling, I can say that so what is the convection resistance? The convection resistance is 1 by HA. Fine. So you know there are many questions like slabs are connected in series, then atmosphere, ambient is here, ambient is present over here, this is L1, this is L2, this is K1, this is K2, here it is T1, here it is T2, here it is T3. So you know that if finally if I have to make a circuit, I have to include all the resistance starting from here. That means Q starting from here, that means 1 by Hi into Ai. A is constant, so A I can write. Then L1 by K1A, then L2 by K2A, then 1 by H2A. So you can, all these things you can write, just you have to remember the value of the thermal resistance and between what 2 points you are applying, right? Suppose I have to find the intermediate temperature, so I can apply between T1 and T2 or the ambient and T2, and I know it's a steady state, so Q will be same throughout. So between any two points you can just use the value of Q and find whatever the question is being asked. My dear friends, now let us discuss the case of heat transfer in cylinders. This was all about plain slab. Now I have to find out, basically when I talk about cylinder I mean hollow cylinder. So what is the situation? The situation is something like this. The situation is something like this. This is R1, this is R2, length of the cylinder. Let's say some fluid is flowing over here, hot fluid is flowing. So how will the heat transfer take place? Radially. The heat transfer will take place radially. So when heat transfer is taking place radially, the element that you will take for analysis, it will be what? A circular element. A circular element you will be taking. Over there you will apply all the analysis which is needed. That means if this is QR at an thickness dr, here the Q will be QR plus dr. Now remember, QR plus dr is equal to what? Using the Taylor series you have to write QR plus dr in terms of QR. I have already told that. So you have to apply the energy conservation equation over here, and you will be getting what? The differential equation, and by solving that differential equation you have to get the temperature. My dear friend, just remember that in the entire conduction, if I tell you, if I talk in brief, my objective is very simple. My objective is to know how the temperature is varying with respect to distance and to find the steady state heat transfer. That's it. If you just able to get this one, then there will be no problem throughout the conduction. So I am not going into the detail that how the analysis is being done. It's very easy, you will be able to know. I am just writing the expression that comes. This is the expression that you get. This is the, I should say, differential equation that you get on applying the energy analysis or energy conservation in this cylindrical element. My dear friends, by seeing this only you will be able to say that what are the assumptions that we have taken. For example, no RHS is there, so it's a case of steady state. K I have taken outside, that means homogeneous isotropic is there, and I have also assumed that K is independent of temperature. Yes or no? Heat generation element is there, so I will not say it is not no heat generation we have assumed. And suppose one assumption if I apply, that no heat generation, so automatically that goes off and we are left with yes or no. And by solving this, see what I told you the objective, by solving this I will be getting the value of T. I want to see that how temperature is varying with respect to radius, and by solving this differential equation I will be getting that itself. Are you able to get it or not? Right? So what was the equation? So can we solve this? The differentiation of this thing is 0, that means this thing must be a constant. That means what is del T by del R? Del T by del R is C1 by R. I can write del T is equal to C1 by R dr. If you integrate this, my dear friends, you will be getting what? C1 ln R plus C2. Yes or no? So how the temperature is varying? The temperature is varying logarithmically. And what is the boundary conditions? At R equal to R1, T is equal to T1. at R equal to R2, T is equal to T2. Now you apply these two boundary conditions, two constants are there, and my dear friends, you will be able to get the temperature profile, the temperature variation with respect to what? With respect to radius. With respect to what? With respect to radius. Getting or not? So although the temperature profile you can put it over here and you can find it, still I am trying to write the final expression of temperature profile. This is the value of temperature profile when it varies with respect to radius. Are you getting or not? Are you getting or not? And my dear friends, finally if I ask you what is the value of steady state heat transfer? Steady state heat transfer will be what? So I am trying to write the final expression. I am trying to write the final expression of heat transfer, steady state heat transfer over here. So what comes, can anyone tell me? Del T is equal to Q is into RTH, and what is the value of RTH? The value of RTH is ln R2 by R1 by 2 pi KL. Yes or no? This is the value that we get. This is the value of conduction resistance that we get. So I hope you are able to get that sir has written directly in terms of resistance concept. So it becomes very easy for you to memorize that what is the thermal resistance in case of a cylinder, ln R2 by R1 by 2 pi KL. Fine. My dear friends, moving on, similarly if I take third case and I try to analyze spheres, what happens? If I try to analyze spheres, what happens? Hollow sphere is what I am talking about. So similarly, you have to just take an element over here. You have to take an element over here. You have to apply all the energy equation over here with generation. And what differential equation you will get? You will get something like this. Yes or no? See, it's so easy to remember. It's so easy to remember if you just find a pattern. So I have not written any assumptions on the board, but by seeing the equation only you will be able to tell that sir what assumptions are there in the equation. Like steady state is there, homogeneous isotropic, K is independent of temperature and all those things. And if I take generation as 0, I will be writing what? This thing. I will be writing what? This thing. Yes or no? Yes or no? So del by, if I suppose I want to find that how temperature is varying, how the temperature is varying. So see, here only I have solved. So let me take it to the next page. Integrate it. So see, after solving the differential equation, what I have got? Can anyone tell me how it is varying? It is varying hyperbolically. What is the expression? T is equal to C1 minus 1 by R plus C2. Yes or no? Sir, two constants are there. That means two unknowns are there. So two boundary conditions I have to apply. What boundary condition? At R is equal to R1, T is equal to T1. At R equal to R2, T is equal to T2, and you get the temperature profile. Yes or no? You get the temperature profile. Here also if I try to write the temperature profile, my dear friends, if I try to write the temperature profile, so how the temperature profile will look like? The temperature profile will look like something like this. See, if you are able, if you can learn, then it's always suggested to learn, but if you are not able to memorize, it's not a problem. This is the temperature profile. You might be wondering that, sir, where they will ask you the temperature profile, that like how the question may come. They can give you that at R1 the temperature is T1, at R2 the temperature is T2, find the temperature at a R, let's say anything. In that case, directly this equation will be coming handy. Anyway, even if you don't remember, you will be able to solve it. That is not the problem. And what is the value of thermal resistance in this case? What is the value of thermal resistance in this case? The thermal resistance is R2 minus R1 by 4 pi K R1 R2. Yes or no? This is the value of thermal resistance in case of a sphere. Rest any question, like they can connect multiple spheres in series and then they will ask you that what is the steady state heat transfer. They will be giving you some different ambients, internal ambient, external ambient, and using that you will be able to find out the value of heat transfer. So all these things are very simple, my dear friends, and you will be able to do it very easily, right? So fine. Now moving on to the concept of critical radius of insulation. Moving on to the concept of critical radius of insulation. My dear friends, this concept comes where? This concept comes in case of a hollow cylinder or a sphere. Yes or no? So suppose this is a cylinder, my dear friends. So solid cylinder also this concept comes, that is not the problem. Let's say only this is R1 and this is, let's say, R. I have put an insulation of, this is the insulating material that I have put over the inner cylinder, and there is some ambient. There is some ambient over here having a temperature T infinity, having heat transfer coefficient as H, and this is the situation. This is the cylinder, my dear. This is the cylinder. So why we study the concept of critical radius of insulation? My dear friends, if I ask you what is the total thermal resistance over here, you will be saying that total thermal resistance is what? Conduction resistance plus convective resistance. What is conduction resistance? Ln R by R1 divided by 2 pi KL. And what is convection resistance? 1 by HA. So 1 by H and the outer area. So it will be what? 2 pi R into L. Now why this concept comes? This concept comes because if you go on applying insulation, this conduction resistance will increase because R is in the numerator, and at the same time if you go on applying the insulation, this will decrease because R is in the denominator in case of a convection resistance. So one is increasing and one is decreasing. So you need to settle it somewhere. You need to get a place where there is some see, one is increasing, one is decreasing. So you need to come to a place now that where something is optimal, the resistance is the heat transfer is optimal, or the resistance is minimum, resistance is maximum, something like this. So whenever there is a talk of optimality, that is maximum or minimum, right? Maximum or minimum, so we have to differentiate it. So what is the case? The case is, suppose this is the total resistance, my dear friends. There is the total resistance, and if I try to differentiate it with respect to R, so what will be the so what will be the differentiation? And put it equal to 0. So after cancelling all these things, my dear friends, you know what you are going to get. The critical value of radius will be what? K by H. the critical radius will be K by H. K of insulation and H of the surrounding, K by H. Similarly, for spheres, this R critical will come out to be 2K by H, 2K by H. So, K by H for cylinders, 2K by H for sphere. What happens over here? This is the heat transfer, this is R. So, heat transfer increases till critical radius and then it falls. So, this area, or if I talk about resistance, resistance becomes minimum over here and then the resistance increases. So, this portion is applicable for cables, wires, and this is applicable for pipes carrying hot water or hot fluid. So, all this comes under theoretical concept. I hope you have taken care of that aspect. So, I am not going to say much into that. Anyway, so this is the concept of critical radius. I hope you have, in exam what you can expect, that for 1 mark they can ask you what is the critical radius of insulation. Always remember, K is of the insulating material, H is of the surrounding. Now, my dear friends, let me talk of the concept of heat generation. Let me talk of the concept of heat generation. Let me talk of the concept of heat generation in case of plane slabs. In case of plane slabs. Okay. In plane slabs. My dear friends, I will be talking about heat generation in plane slab, and the same concept will be extended to cylinders and spheres. Fine. See, only difference is initially I was taking this equal to 0, but now since it is heat generation, I have to consider this element in my equation as well. And this is a differential equation. If you solve this differential equation, you will be getting the profile that, see, I told you that what is my objective? My objective is when there is heat generation in plane slab, how the temperature is varying. That's it. That's it. And steady state is there. Yes, steady state is there. Right hand side is not there, so steady state will be there. Material homogeneous, isotropic, K independent of temperature, all these things will be there, right? But just try to get that whenever in the examination, in the question, you have to see that what they are saying, heat generation is there, steady state is there, no unsteady state is there. Accordingly, you have to change the equation. Now, suppose you have to solve this, my dear friends. Suppose you have to solve this. So, how will you solve? You have to solve this differential equation. Yes or no? So, what I can write? Yes or no? This is how I will solve. So, suppose I have integrated it. And again, if you integrate it, see, so easily I am able to get the variation of temperature with respect to x. I can clearly say that how temperature is varying with respect to x? Parabolically. Parabolically. So, my dear friends, just see that what they are asking in the examination also. Suppose they are saying that temperature varies with distance with heat generation given linearly, parabolically, exponentially, logarithmically, whatever. So, just don't just don't remember that always it will be linear. It can be parabolic also, given that there is heat generation. Suppose when it is linear, when there is no heat generation, the variation will be what? Linear, as we have seen in the earlier cases. Getting or not? My dear friends, how many constants are there? 2 constants are there. So how many boundary conditions will be required? 2 boundary conditions will be required. Yes or no? Suppose if I talk of the case of, now here you study some cases na, that equal temperatures at both the phases, equal temperature at both the cases. What is this case? This case is you consider x equal to 0 over here, x equal to plus L by 2 and x equal to minus L by 2. This is Ts, and here it is maximum, so it will be T max. So from maximum to minimum the heat flows. So what will be the direction of heat flows? Over like this and like this, like this and like this. If I ask you what is the total heat generated, it will be Q generation into the entire volume, which is A into L. If I ask you, see, in the middle heat generation is taking place, so 50% will go in the right side, 50% will come on the left side. Yes or no? So if I ask you over here how much heat has come, Q total heat generated by 2. Over here in the left face, Q total heat generated by 2. Getting or not? So suppose that equation is there with you. Which equation? Q generation x square by 2k plus C1x plus C2. Which equation? This equation. So what are the boundary conditions, my dear friends? What are the boundary conditions? The boundary conditions will be what? At x equal to 0. See, temperature is maximum, so slope will be 0. So it will be dt by dx equal to 0. And at x equal to L by 2, the temperature is Ts. So you put these boundary conditions over here and you will be getting an equation. Yes or no? You will be getting an equation, and you keep on memorizing that equation. What is the equation? Something Q generation by 2k L square by 4 minus x. Something like this the equation comes. Yes or no? So my dear friends, yes, you can memorize this equation, that is no fault over here, but you should understand that from where the concept is coming. And most importantly, see, this is the case that I have taken, this is the case that I have taken, that in the middle the temperature will be maximum, and here it is Ts and here it will be Ts. So tell me one thing, from the right hand side, see, 50% heat is going in the right direction and 50% is going in the left direction. So if I ask you in the right phase, at the right phase, how much heat has come, you will say that, sir, it is Q generation AL divided by 2. See, 50% of the total heat generation on the right phase, the heat has come. This is equal to the heat convected from the right phase. Yes or no? Heat convected from the right phase. So it is what? HA, and let's say the temperature is Ts minus T infinity. So A and A gets cancelled out. Yes or no? So Q generation L by 2 H plus T infinity is equal to Ts. So this is another equation, my dear friends, that you people memorize. No harm in memorizing, but you should understand that how these equations are coming. What have I applied? I have applied only simple concept that, yes or no? I have applied only simple concept that whatever is the heat generation will be convected from the surface. Whatever is the heat generated will be convected from the surface. Getting or not? So these two equations are there, and very easily you will be able to find whatever they are saying. Now suppose there is cylinder. So you have to understand that whatever is the solid cylinder is there, whatever is the heat generated in the volume pi r square L, whatever is the heat generated in the entire volume will be convected from the surface, will be convected from the surface 2 pi r L HA, and delta T is what? Ts minus T infinity. That's it. That's it. That's it. You apply this concept and you solve any problem, whether it is of a sphere, whether it is of cylinder. So just know that how the equations are, we are coming to equations. So that being said, my dear friends, I am not going into much detail of cylinders and spheres, because it is the same concept that is followed everywhere. You just have to know the concept, and rest equations I know that you have by hearted, right? So why I am saying all this, just in case you forget the equations in the examination hall, by using concept also you will be able to solve it. So this is the, I have talked about critical radius. I have talked of critical radius. One small question is there for you guys. I am expecting you guys to answer in the chat box, that whenever you get the answer, that why there is no critical radius of concept, critical radius of insulation concept in case of plain slab. This is the question for you. We have studied in cylinder, we have studied in sphere, why it is not there in case of a plain slab. So I am expecting everyone to answer once you get the result. So my dear friends, these are the concepts. So in case of cylinder, in case of conduction, I have told you so many things in the last 45 minutes, 50 minutes. 3D conduction equation, then spheres, then cylinders, thermal resistance concept, so many concepts I have told you, my dear friends. And now it is the time that I talk about lumped analysis, right? I talk about lumped analysis. So just let me drink some water. So have you studied this lumped analysis concept? So my dear friends, see, generally temperature varies with respect to x, y, z and t. Over here we will consider that temperature varies only with respect to time. That means no spatial distribution will be there, x, y, z variation is not there. For example, if I consider this small body, suppose throughout it the temperature is 120 degrees centigrade, 120 degrees centigrade at, let's say, T is equal to 0. After some time at T is equal to, let's say, T1, with time the temperature will fall. So let's say it is 90 degrees centigrade, 90 degrees centigrade, 90 degrees centigrade. So throughout the temperature is uniform, it is uniform, but it is varying with respect to time. So such cases will be considered under lumped analysis. Getting or not? That means unsteady state. In a way we are dealing of unsteady state. So my dear friends, you know that we start this topic. How do we start this topic? By expression of temperature with respect to time for a body heating or cooling, whatever, heating or cooling. So what is the expression, my dear friends? We are not into derivation, but what is the expression? Yes or no? What is H? Heat transfer coefficient of the surrounding. What is T? At any time temperature of the body. T infinity ambient temperature, Ti initial temperature, rho density, V volume, Cp heat, specific heat capacity. So this is the expression that everyone is expected to Memorize, my dear friends. So what is the expression used for? For you put any value of time over here and you will be getting the temperature which is here. Given all these things are given to you. Fine. Now another concept comes of bio number. What is bio number? See, for the lumped analysis, whether lumped analysis is applicable or not in any question, we consider bio number. We say na bio number should be less than 0.1. So what is bio number? Internal conduction resistance by external convection resistance. Internal conduction resistance. So suppose a plane slab is there. Suppose a plane slab is there. This is T1 and this is T2. This is L and this is A. So what is conduction resistance? It is L by Ka. What is convection resistance? See, convection is happening from here. 1 by Ha. So finally what we are getting? HL by K. HL by K of solid. HL by K of solid. Now why I am saying HL by K of solid? Because after some time when I will be discussing Nusselt number, there is K of liquid. My dear friends, we say that for lumped analysis, to be applicable, this bio number should be very small, like less than 0.1. We say that we can apply the, what we can apply? We can apply that expression. We can apply this expression, right? So I am not going into the theoretical details. I am expecting all of you to take care of that. My dear friends, whenever, see, till now I will be giving you some hint of Heisler charts here. Till now I have not considered that temperature is varying with respect to distance. But suppose if we consider that temperature is varying with respect to distance and time it is varying only, that means temperature and time, then the concept of Heisler charts comes into picture. In a plane slab, they will ask you that at this much x, at a particular distance x, what is the temperature? At this much x, what is the temperature at a given time? So whenever time concept comes, Fourier number comes into picture. Whenever time concept comes, Fourier number comes into picture. Alpha T by LC square. Alpha T by LC square. Yes or no? Alpha is the thermal diffusivity, LC is the characteristic length and T is the time. So Fourier number is there, that means time concept is there, and with respect to x, spatial distribution is also there. So when two things come, means temperature is varying with respect to two parameters, that means distance and time, then the concept of Heisler charts comes into picture. And if you are able to get this thing, rest the concept is given in your Cengel, you will be very easily able to go through the concept once. If you are, I have covered this thoroughly in my class, but still if you are not able to get, you can ask me anytime, right? So I am not teaching that, because in the exam what they will give? They will give you the charts, they will give you the table in the table format, not graphical format. Table format they will give you, lambda 1 and A, the two constants are there, and using that you will be able to find the heat transfer and you will be able to find the temperature. Two things they will ask you to find out. Now my dear friends, in bio, what is the HLC by K? Here alpha T by LC square. What is LC? LC is the characteristic length, volume by surface area, volume by surface area. Suppose slab is there, volume is what? A into L by A, LC equal to L, given that heat transfer is taking place from one side of the slab. Suppose they tell you that heat transfer is taking place from two sides of the slab. So here you will put what? A into L by 2A, and that is L by 2. So in the previous case that we have taken, we have discussed that heat transfer is taking place only from one side of the slab. Similarly for sphere also will be able to find out. For any, for sphere what will happen? For sphere it will be 4 by 3 pi r cube divided by 4 pi r square. So r by 3 you will get as the characteristic length. So any object they give you, you will be very easily able to find the characteristic length. But you should know that in Fourier's number and in bio number, this LC is what? This LC is characteristic length. Not only here, in Nusselt number also, when I will be talking, this LC is nothing but your characteristic length. Fine. So all this concept we have talked of. All this concept I have talked of, and now my dear friends, it's time for us to go into fins. It's time for us. So have you studied the concept of fins? Have you studied the concept of fins? What is there in the concept of fins? Can anyone tell me? See, so many assumptions are there in the beginning of the problem. I am only telling you what is the concept of fins. See, it is attached to this body. It is attached to this body. The temperature of this body is T0, base temperature. From here conduction starts, and from here your heat is transferred by convection. Yes or no? Now what happens? When you go in the x direction, your temperature starts to fall. For example, over here at this section, it will be, let's say the base temperature is 90 degrees centigrade. So over here, as you go ahead, it will be, let's say, 60. If you go some distance more, it will be, let's say, 40. Some distance more, it will be, let's say, 35. So the temperature falls, and let's say your ambient temperature is 25 degree centigrade. So my dear friends, when you have to analyze a fin, see, I have already told you that what is our main purpose? The main purpose is getting a temperature distribution and getting the amount of heat transfer. That's it. So if you have to analyze fins, let's say you will be taking this something like this, a section from the middle. You have to cut this section from the middle, and you will be analyzing this over here. So you will be saying that, let's say at this face, at a distance x from here, the heat is qx. At a distance now x plus dx, the heat is qx plus dx, and from the above surface, from the below surface, from the side surface, it is heat is being convected. So you have to understand that what is the situation. The situation is heat is being conducted throughout length, but at the same time it is getting convected also. No heat generation, steady state, all these assumptions are there in fin. So if you keep all these things in mind, I am not going to much detail, my dear friends. I am just giving you an idea that if you have read this, you will be able to very easily connect what I am trying to say. So if you apply this energy conservation equation, my dear friends, finally you arrive what? You arrive at this equation. Again, see, same concept, same logic is there. In the last 1 hour, what I am doing? I am applying energy conservation equation, and I am reaching at a differential equation. And solving that differential equation, you will be very easily able to get what is the temperature profile, yes or no? Or the heat transfer, yes or no? So over here, you, in case of fins, you reach over here. Del 2 theta by del x square minus m square theta is equal to 0. Can anyone tell me what is theta? Theta is the temperature difference with respect to ambient. What is m? M is root over HP by KAC. What is P? Perimeter. What is AC? Cross section area. That means P and AC is there for cross section. H is of the surrounding, heat transfer coefficient of the surrounding. K is the conductivity of the material thermal conductivity. My dear friends, it is see it is what? It is a second two-dimensional second order differential equation. So how many unknowns will be there? Two unknowns will be there. This is from maths, my dear friends. So if I ask you what is the theta expression, C1 e, see what are the roots of this? The roots will be d is equal to plus minus m. So you know na, C1 e to the power m x plus C2 e to the power minus mx. Yes or no? And by maths you also know that this can be written in this way. I can show you how it comes, but right now I am only saying that yes, it happens. I hope you know this, how it is coming. So how many concepts, how many constants are there? C1 and C2. Using boundary condition, I will have to, using boundary conditions, I will have to apply the conditions and get the value of C1 and C2, or A and B. So sometimes I'll use this expression, sometimes I'll use this expression, but you should know in the back of your mind that using both the expressions only, I'll be getting the same result. Yes or no? Okay. So other things, keeping other things aside, you know that two conditions are required. Three cases we discuss. What are the three cases? Infinitely long fin, adiabatic fin tip, and the third case, which is general case. In all the three cases, one condition is fixed. And what is that condition? The condition is at x equal to 0, T is equal to base temperature. So theta is equal to T naught minus T infinity, and that is nothing but T naught, theta naught. In all the three cases, this condition is constant, and the second condition is different for the three cases, and it is about the second boundary condition that we have to study the three different cases, and we'll be applying that, and you'll be getting a different set of temperature profile or heat transfer or whatever. That's it. So what is the first case? Infinitely long fin. Infinitely long fin. What happens, my dear friends? Suppose this is a fin. See, if I take a very long fin, what will happen? That let's say the base temperature is 90 degrees centigrade and ambient is, let's say, 35 degrees centigrade. So if there is a very long fin, at the end of the fin, I will be reaching this ambient temperature. Yes or no? So what is the case? The case is at x equal to L, theta is equal to 0, because theta equal to ambient minus ambient is 0. So that is the case, my dear friends. First, I have already told you one boundary condition. This is second boundary condition. You apply this, you get the equation. That's it. Theta is equal to C1 e raised to mx plus C2 e raised to minus mx. Yes or no? So my dear friends, you apply all these boundary conditions and finally you arrive at what? Theta equal to theta naught e raised to minus mx. Yes or no? Yes or no? And can you say how the temperature is varying? It is varying exponentially. It is varying exponentially. Now Q, theta is what? Theta is T minus T infinity. Theta naught is what? T naught minus T infinity is equal to e raised to minus mx. So we got na temperature variation with respect to x, and that is exponentially. Finally, if I ask you what is Q? What is Q? So remember, we always find heat transfer from at the base. At the base we find the heat transfer. And see, for finding heat transfer in case of conduction, we have to apply what? Fourier's law, minus Ka dt by dx, where? Minus Ka dt by dx, where? At x equal to 0. See, dt by dx or d theta by dx, it's same na? dt by dx if I write, or d theta by dx if I write, it will be same only. So at x equal to 0, and if you apply this, you will be getting what? You will be getting root over HPKAC into theta naught. Are you getting or not? HP root over HPKAC into theta naught. So see, H is constant, P is constant, K is constant, AC is constant, theta naught is also constant. It means it's a steady state only. One value of Q throughout, steady state only. Getting or not? Second, insulated fin tip. Insulated fin tip or adiabatic fin tip. So hi Meet, I hope your preparation is going good. So what is about insulated fin tip? Insulated fin tip means what? The tip of the fin is insulated. No, we don't insulate a fin, because when you have to increase the heat transfer, why would we insulate the fin? Yes or no? The heat transfer, we assume that suppose when heat is getting conducted here, its purpose is to get convected from here. So from this portion, the heat convection is so small, it's so minute that we found it very comfortable to just ignore this and get a boundary condition. So what we do? So Q convected is equal to 0. So Q conducted is 0, that means minus Ka dt by dx at x equal to L is 0. Minus Ka dt by dx at x equal to L equal to 0. K and A cannot be 0. So dt by dx at x equal to L is equal to 0. I told you dt by dx and d theta by dx both are same only. So d theta by dx at x equal to L is equal to 0. You put this boundary condition, apply there, and you get, see, it's all about getting a boundary condition. I have applied there and I will be getting a temperature profile. See, one temperature profile, one boundary condition is already mentioned. I have mentioned in the beginning. What? At x equal to 0, theta equal to theta naught. This is the second boundary condition. After applying both the boundary, again, here in this case, theta is equal to A cos hx plus B sin hmx plus sin h mx. I will be using this profile, I will be using this variation for getting the temperature profile in the second case, that is in this case. So what happens over here? Theta is equal to theta naught cos hm L minus x divided by cos h ml. So I hope you know that we get this variation. So thank you Uttarakhand with us. I am afraid of mathematics. Don't worry Ankit. Don't worry, we will sort it out. Okay. So what I am saying is that this is the variation of theta with, this is the variation of theta with respect to x. And can anyone tell me what is the Q variation? Can anyone tell me what will be the Q variation? The Q variation will be root over HP tan h ml. So just remember my dear friends that only this extra term of tan h ml comes into picture. Only this extra concept of, expression of tan h ml comes into picture, and if you remember, it's a steady state only. It's a steady state only. It's a steady state only, yes or no? It's a steady state only. So this is what? This is the expression of Q, and this is what? The variation of theta. This is the variation of theta with respect to x. So all these concepts are there. Value of h. What is value of h? My dear friends, it is hyperbolic, na? Arey Aman, it is hyperbolic, na? In calci, you will put hyperbolic and then you will apply tan and then you will get, na? Arey, getting or not? Hyperbolic. Clear? Tan hyperbolic. See, this h and this h are different. Don't get confused. Yes, correct, Sarath. It is hyperbolic. Now the third case, my dear friends, case 3. Case 3 means convection from the tip. Convection from the tip. Convection from the tip. Convection from the tip. See, earlier we used to ignore the heat transfer from this small part, from this tip part, but now we are not going to ignore this. We are going to consider this also, because earlier we are used to we were committing some error, let it be 2%, but we were doing some intentional errors. Now we have to take care of that error. That means we are going to assume that convection is taking place from here. Convection is taking place from here. Minus Ka dt by dx at x equal to L, and this is equal to convection. So HA, let's say the temperature over here is Ts minus T infinity. Ts minus T infinity. So you apply this equation and you will get a boundary condition. You will be applying this long equation, that Q conduction equal to Q convection from the tip, and you will be getting one. So it seems to be a long process. If you apply this, it will be a long process. So to cut the long process short, what happens? The concept of corrected length comes into picture. What is the concept of corrected length? The concept of corrected length is, I'll intentionally increase some length and I will assume that it is a case of insulated tip. I'll intentionally increase some length, I will let the extra heat flow from here, and then I will apply the case of insulated tip, that is your case 2. Now whatever this extra is there, we call it a corrected length. So in case of plain slab, LC will be what? L plus T by 2. See, L is your previous length, and this is, let's say, del L. So L plus T by 2, it is for K. T is what? T is the thickness. And in case of cylindrical fin, LC will be L plus D by 4. So just remember these two cases of corrected length. And what happens after you get the C, after you get the value of LC, you simply go and substitute wherever L you are finding. Wherever L you are finding, you are going to substitute by LC in the second case, and you automatically get the cases for the third one. Getting or not? Are you getting or not? We have founded the corrected length over here, and in the second case you put L equal to LC and you get all the values of heat transfer, variation, temperature profile, and all those things. Now my dear friends, the question is, let's say they have not given you which case it is. Let's say they have not given you which case it is. So mostly, see, if no information has been given to you, you have to simply apply the case 3. That means apply the case of corrected length. Yes or no? If no information has been given to you, you have to apply the case of case 3. And most of the times you will be getting insulated or infinitely long indirectly in the question, right? Okay, Sarath is asking, sir, what if LC is given, rectangular duct is given? See, I'll tell you one thing. A general formula of corrected length 4 AC by P. A general formula of corrected length 4 AC by P, 4 times area of cross section by perimeter cross section. You apply this and you get any cross section you get. Sir, it is clear or not? Sarath, 4 AC by P, 4 times area of cross section by perimeter, and you apply this and you get for any cross section. Fine. चलो ठीक है. Now my dear friends, let's talk on performance parameters. Performance parameters में क्या, what happens? Fin efficiency, and fin effectiveness. Now my dear friends, what is fin efficiency? Fin efficiency is what? Q times of actual divided by Q times of maximum. Yes or no? Q times actual and Q times maximum. See, actual you have already found out. Yes or no? Actual heat transfer we have already found out. Now what will be maximum heat transfer? Maximum is, let's say I am explaining you, let's say that this is your fin. Now when will Q be maximum? Q will be maximum when your entire fin has been maintained at T0, 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 T0 and T0. Yes or no? See, if entire fin has been maintained at the base temperature, then only maximum heat will take place from each and every section, because as we go along the length of the fin, the heat transfer decreases as we go ahead. So if we maintain the same temperature T0 at the entire fin, the heat transfer will be maximum. Yes or no? So what will be Q max? Q max will be HA T0 minus T infinity. Yes or no? Q actual we already know, no issues. So let us go to the next page. It is what? Q actual divided by Q maximum. Now if I take the case of infinitely long fin, what happens with Q actual? HP KAC theta naught. Yes or no? So what will be? It is root over HP KAC theta naught divided by Q max is what? Q max H A and T naught minus T infinity is nothing but theta naught only. Also A I can write perimeter into length. Yes or no? A I can write perimeter into length. So it is HP KAC divided by H perimeter into length, and theta naught gets cancelled. My dear friends, it will be what? It will be root over. It will be what? L is outside. H and HP. So KAC by HP and into 1 by L. So this term is what? M. 1 by M rather. So your efficiency will be what? 1 by ml. Your efficiency will be what? 1 by ml. 1 by ml in case of what? Infinitely long fin. And if I take the case of insulated fin, if I take the insulated fin tip, so efficiency is what? Q actual divided by Q maximum. So you know that, see, in heat transfer only tan H ml only the term of tan H ml is extra. Yes or no? So if you apply all these things, you will be reaching at 1 by ml into tan H ml. This extra term will be there. And for the third case, you know that L is equal to LC. So I am not going to tell you much further in that. My dear friends, the second performance parameter is fin effectiveness. What is fin effectiveness? Fin effectiveness is Q with fin divided by Q without fin. Q, see, when I am putting fin, I am expecting more heat transfer to take place. When I am putting fin on any surface, I am expecting more heat transfer to take place, yes or no? So this term must always be greater than 1. In fact, this term should always be greater than 2 for the fin to be effective. So let's say without fin, I have not put any fin, so what happens? The Q with H A of the base, and T naught minus T infinity, this will be my heat transfer, and Q with fin I already know, yes or no? So if you take the case of infinitely long fin, what is effectiveness? Q with fin root over HP KAC theta naught divided by HAB base into theta naught only. Theta naught gets cancelled. So it will be what? PK by HA. AC is equal to AB. See, AC is equal to AB, so it gets cancelled out. AC is equal to AB only. So PK by HA, yes or no? PK by HA. So this is the formula for effectiveness. Now you tell me, my dear friends, when will effectiveness increases? Effectiveness gets increases when your K is high, that means highly conducting material you have taken, then your effectiveness increases. Second, H is low. We always say that we will install fin in case of a low H condition. Then only fin, there is some advantage of putting fin. And finally, what do we say? P by A ratio should be more. That means what? We say that thin fins should be installed. The rest, my dear friends, you will be able to make it out in any case of theoretical questions. So that brings, my dear friends, the entire conduction chapter to an end, starting from the 3D generalized conduction equation to the concept of fins. I have discussed all the important formulas, my dear friends. Yes or no? And next we will be starting with radiation. Right? But after a 2 minutes break. Fine? So hello my dear friends, let's again start the session. So is the audibility visibility clear my dear friends? Fine. So my dear friends, in radiation we are back with radiation. In radiation, the chapter starts with some basic concepts. And after that it goes into the network models. Yes or no? So let's start with some of the basic concepts and finally we will be entering into network model. Just yes or no? So what happens in radiation my dear friends? The it's a kind of electromagnetic wave. It travels with the speed of light. All these things are there. It deals with, we are interested in thermal radiation, and thermal radiation corresponds to a wavelength of 0.1 micrometer to 100 micrometer. Yes or no? So the first term that comes into picture is total hemispherical emissive power. What is total hemispherical emissive power? Total energy radiated from, total energy emitted from a surface per unit area per unit temperature, per unit area per unit, no, not per unit temperature, only per unit area is the total hemispherical emissive power, total heat emitted from the surface per unit area per unit time. Second is the concept of emissivity. What is the concept of emissivity? Emissivity is the hemispherical power of any body with respect to the emissive power of a black body. See, why we are using the concept of black body over here? We are using the concept of black body because at any given temperature the black body emits the highest radiation. At any given temperature the black body emits the highest temperature. That is why we use the concept of black body. So black body is a perfect emitter, maximum absorption capacity, maximum absorbing capacity, diffuse in nature, diffuse in nature. So what is emissivity? For any non-black body, it is the ratio of total hemispherical emissive power divided by the black body emissive power is called the emissivity, and obviously its value will be less than, it will be in between 0 to 1. Next is, if I apply just monochromatic over here, if I apply just monochromatic hemispherical emissive power, monochromatic term, if I apply monochromatic hemispherical emissive power, so it will be nothing but per unit wavelength. Now I am talking with respect to per unit wavelength. Same in case of monochromatic emissivity. Monochromatic emissivity, let's say E of lambda if I am talking about, so it will be monochromatic hemispherical emissive power of any body with respect to the black body. Okay, that means per unit wavelength I am talking about. See, what is monochromatic hemispherical emissive power? I am just telling you one thing. Let's say E of lambda graph is given something in this way, and this is the lambda, and suppose this is, let's say, lambda 1, and suppose this is, let's say, lambda 2. So if I simply integrate this, or if I simply find the area of this curve, if I simply find the area of this curve, that means E of lambda d lambda from the limits lambda 1 to lambda 2, I am going to get what? I am going to get E of B. That means total hemispherical emissive power I will be getting if I integrate the monochromatic one. I hope you are getting this. I hope you are getting this concept. Now what happens, my dear friends? For grey body, for grey surface, E lambda is equal to E. Monochromatic emissivity is equal to hemispherical emissivity for a, that means E lambda is constant. E lambda does not changes for what? For a grey surface. So just remember this. Yes or no? So these are some of the important terms, my dear friends. Now you know that, let's say, let us understand some of the important terms. Let's say this is any surface. Let's say this is any surface. Some 100 units of energy is incident. So some part will be reflected, some part will be absorbed within itself, and some part will get transmitted. Let's say 25 units is getting transmitted, 50 units is getting absorbed, and 25 unit is getting reflected. So what will be reflectivity? Reflectivity will be fraction of energy which is reflected divided by total energy coming, which is 0.25. What is absorptivity? Fraction of energy absorbed by total energy incident, which is 0.50. What is transmissivity? Same, fraction getting transmitted by total, which is 0.25. So always remember, for any body, alpha plus rho plus transmissivity is equal to 1. Now in our heat transfer, in the materials or the bodies that we are going to discuss in this chapter, they are mainly opaque, and when they are opaque, the transmissivity becomes 0. That means for opaque the transmissivity is 0. So what happens? Alpha plus rho is equal to 1. Alpha plus rho is equal to 1. Yes or no? Yes or no? So what happens later on when I write alpha in place of this, I can write 1 minus rho. So all these things are there, my dear friends. Yes or no? Now there are some laws of thermal radiation, some important laws of thermal radiation. Some of the important laws of thermal radiation, it is there. First is Kirchhoff's law. Can anyone tell me what is Kirchhoff's law? For suppose any body is there in any enclosure and they are at thermal equilibrium with each other. So alpha is equal to E. That means alpha is equal to emissivity. Absorptivity is equal to emissivity. Yes or no? Kirchhoff's law. For any body with thermal equilibrium with its surrounding, alpha is equal to emissivity. Fine. Now some laws are there which is specifically for black bodies. Some laws are there which are specifically for black bodies, and what comes? Planck's law, then Wien's displacement law, Wien's law, and finally Stephen's law or Stephen-Boltzmann law. So starting with, what is Planck's law? What is Planck's law? My dear friends, Planck's law tells us about the, see, expression you have to remember, yes, but what it is telling, it is also important. Planck's law tells us about the monochromatic emissive power of a black body. Monochromatic emissive power of a black body, and it tells us that it is a function of temperature and wavelength. Now this is what? Absolute temperature. Absolute temperature. See, absolute temperature, always remember, in radiation, everywhere the temperature is in Kelvin. Just remember this thing. In radiation, everywhere the temperature is in Kelvin. So E lambda is a function of, now see, I will be writing the expression of E lambda. See, E of B lambda also you can write, B is signifying the black body. So that expression I am writing over here, and it's up to you whether you want to memorize it or not. It is up to you whether you want to memorize it or not. Obviously, when it is monochromatic, so the unit will be watt per meter square micrometer. See, wavelength is being denoted by micrometer in case of radiation. Okay. So this is what? Planck's law. So I am sure that everyone has gone through this graph, that whenever the temperature increases, the point of maximum energy shifts to the right. Lambda 1, whenever the temperature increases, the point of maximum energy shifts to the left. Yes or no? Have you gone through this graph or not? Let's say this is T1, this is T2, this is T3, and T3 is greater than T2 is greater than T1. So, and this product, the lambda at which energy emitted is maximum, the lambda at which energy emitted is maximum, and the temperature. So lambda m, let's say I am writing lambda m into T, is equal to constant, and this is nothing but your Wien's displacement law, or in simple, if I have to say, this is your Wien's law. The constant value is there, some 2838 micrometer Kelvin. So it's up to you whether you want to memorize it or not. But as far as my concern is there, I think they will be giving the all the values. Here also C1, C2 values, no need to memorize, they will be giving you. Here you can memorize. Here the value of constant in case of Wien's you can memorize. Okay. ठीक है. Now what is Stephen-Boltzmann law? The next, see, this is also for a black body. This is also for a black body. This is also for a black body. ठीक है. Now what is Stephen-Boltzmann law? Stephen-Boltzmann law. See, few minutes back I told you that Meet, what is the value of C? Check your notebook. What is the value of C? Tell me what is the value of C? Some 2838. I don't remember right now, but it should be somewhat like 2838 micrometer Kelvin. 2898, correct. 2898, correct. 2898, correct. 2898. Yes. So what is Stephen-Boltzmann law? See, few minutes back I told you that when you integrate the monochromatic hemispherical emissive power, we get the total hemispherical emissive power. Yes or no? So this was monochromatic only. Planck's law was talking about monochromatic only. So when you integrate it with respect to lambda, you are going to get the total emissive power for a black body. See, this was also for a black body, and if you integrate it between 0 to infinity, it will be for a black body only. And see how such a big expression was there in case of Planck's law. You put it over here, d lambda 0 to infinity, and the expression that you will be getting is sigma t to the power 4. Sigma t to the power 4, and obviously its unit will be what? See, earlier your unit was what? Watt per meter square micrometer. Now micrometer is gone, so watt per meter square. And this is your Stephen-Boltzmann law. Stephen-Boltzmann constant 5.67 into 10 to the power minus 8. This is Kelvin to the power 4. So just remember that integrating Planck's law will be getting Stephen-Boltzmann laws, EB equal to sigma t to the power 4. Now you have got the what? You have got the hemispherical power for a black body. And suppose if I have to find for a non-black body, what I have to do? For a non-black body, simply multiply with emissivity. Yes or no? Simply multiply with emissivity. So emissivity sigma t to the power 4, and you get for a non-black body. Suppose they are asking in terms of what, so multiply by area, you will be getting in terms of what. So all these things, my dear friends, are there in your basic concepts and basic, basic terms, understanding basic terminologies. Yes or no? Now let me tell you the concept of shape factor or view factor or configuration factor. It is a geometrical factor independent of temperature, and suppose my dear friends, this is one body and this is another body, A1 and A2. Suppose that 100 units it is emitting. So all 100 will not reach here. Let's say 60 is being reaching over here. So what will you tell? Fraction of energy reaching second body emitted by 1 is nothing but your f of 1, 2, and that is nothing but 60 by 100, which is 0.6. Similarly, let's say this is emitting 100 and only 50 is reaching over here. So fraction of energy emitted by 2 reaching 1 is 50 by 100, and that is nothing but 0.50, and that is the view factor. So what is your view factor? View factor is fraction of energy reaching the second body and emitted by the first body is nothing but your view factor, right? Or configuration factor. So see, what are the rules over here? The rules over here is what? Reciprocity relationship. Sir, please solve one example of shape factor having two plates having 25 degree. This is not a numerical session, this is a revision session, but you can apply the formula of 1 minus alpha by 2 and you will be getting the answer. Okay, you can try with the formula of 1 minus alpha by 2 and you can let me know that what is the answer. Alpha over here is 25 degrees, so 1 minus 25 by 2, you should get the answer. Anyway, in case you don't get, you can just ping me anywhere, I'll be telling you. Anyway, what is reciprocity relationship? Two bodies are there. This is A1, this is A2, this is F12 and this is F21. So what happens? A1 F12 is equal to A2 F21. Yes or no? This is what? This is the reciprocity. This is the reciprocity relationship. Yes or no? A1 F12 is equal to A2 F21. Suppose this is a circular shape and a kind of a hemispherical covering is there. Its radius is r. This radius will also be r. So suppose this is body 1 and this is body 2. So what happens? What is F11 over here? F11 is 0. What is F12? It is 1. What is F21? I don't know. What is F22? I also don't know. So here I can apply reciprocity relationship. So what is A1? F12 is 1. F21 into A2. So what is F21? F21 is A1 by A2. What is A1? Pi r square. What is A2? 2 pi r square 1 by 2. What is F22? F22 will be 1 minus F21. So 1 minus 1 by 2 and it is nothing but 0.5. Are you getting or not? For example, I take one sphere, I take another sphere, something like this. Let's say its radius is r. Let's say its radius is 3r and they are asking you find, this is body 1 and this is body 2. They are asking find F21 or find F22. How will I find out? See, it is a spherical, it is a convex surface, so F11 will be 0, F12 will be 1. So apply reciprocity. A1 F12 is equal to A2 F21. F21 will be what? A1 by A2, because F12 is 1. A1 is what? area of sphere is 4 pi r square. So 4 pi r square divided by 4 pi 3 r square, it is nothing but 1 by 9. So what will be F22? F22 will be 1 minus 1 by 9, which is nothing but your 8 by 9. So these are some of the examples of, where you can apply reciprocity relationship. Now what is summation rule? What is summation rule? My dear friends, summation rule applies for where n surface enclosures are there. N surface, for a n surface enclosure, for a n surface enclosure, what happens? F11 plus F12 plus F13 dot 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 plus F1n is equal to 1. Similarly, for the second surface, 21 plus 22 plus 23 plus dot 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 F2n is equal to 1. And similarly, for the nth body also you can write this. That means the sum of the shape factors is nothing but 1. It can be used for more than 2 plates. Of course, I have written what? N surface enclosure. So more than 10 plates also it will be applicable. But don't forget that for any 2 surfaces, the reciprocity relationship still holds. Suppose 10 surfaces are there. So for all the surfaces, I will be able to write summation rule? Yes, sir. And suppose randomly if I take any 2 surfaces, reciprocity will be applicable there also. So you can use the relationships in this way. So all these things are there, my dear friends, and see, many results are there in view factor, but I tell not to memorize so many results. Just remember the basics and apply in the examination hall. So all these things are there, my dear friends. And now let me come to the most important parts in radiation, and that is your radiation network. Let me come to the most important part in radiation, and that is your radiation network. Radiation network. My dear friends, now everyone be focused from here, because from here question is definitely going to come. From here question is definitely going to come. Suppose this is the body. This is a body. For simplicity I am considering flat only. This is the total energy incident and some energy is being leaving. So total energy incident is nothing but your irradiation. What is irradiation? Total energy incident on a surface. Let's say I am denoting it by G. Now total energy leaving is called what? Radiosity, and that is given by J. Now understand one thing, this total energy leaving is what? Some energy will be emitted also. Some energy will be emitted also, and some energy will be reflected from this G. So what will you write? You will write rho into G plus energy emitted. Now you will be asking one thing, that sir, is it for a black body or for any body? This is for any body. This radiation network concept is for any body. Okay? It is for any body. So what is radiosity? Radiosity is E plus reflectivity times G. What is E? See, now if I have to, now what I will do, this is for any body, but now I will convert it in terms of black body. How? By multiplying with emissivity. Getting or not? Let's say the emissivity of this body is E epsilon rho G. My dear friends, from Kirchhoff's law, from Kirchhoff's law, what do we know? Alpha is equal to emissivity, and most of the bodies here are opaque only. So alpha plus rho is equal to 1. Yes or no? Alpha plus rho is equal to 1. So alpha equal to emissivity. So rho plus emissivity is equal to 1. Rho is equal to 1 minus emissivity. So in place of this, you can write what? Epsilon into EB plus in case of rho I can write 1 minus epsilon into G. So till here are the concepts clear, my dear friends? Till here it is clear? In radiation, this is what radiosity and this is what radiation. Now suppose, my dear friend, if someone asks you that what is the net heat transfer, some energy is coming and some energy is going. So if I ask you what is the net heat transfer, you will tell that, sir, radiosity minus irradiation into the area. This is the net radiation heat transfer. Sir, are you getting or not? So see, just a minute. J value I already have, G value I already know, G value is there. So J minus G into A, J minus G into A. If you put all these expressions, my dear friend, G also in terms of, now you will ask me, sir, how will I write G in terms of J? Sir, J is equal to rho into G plus epsilon into EB. So G I can write now from here, G in terms of J. So converting G in terms of J and J also means all these things, if you convert and put it in this equation, you will be getting what? Sirs, EB minus J divided by 1 minus epsilon by epsilon into area, and this is the concept that you are advised to note it down. My dear friends, this, what is this? Surface thermal resistance, 1 minus epsilon by epsilon A. Why surface resistance? For any surface it will exist. For any surface it will exist. That is why it is called surface resistance. Sir, are you getting or not? EB, sir, in this expression, what is J? Radiosity. What is EB? For a black body. For a black body. Sir, then only I will be able to write sigma T to the power 4 for this black body. Sir, are you getting or not? Next. Now comes this concept of space resistance. Suppose this is one body and suppose this is another body. This is body 1 and this is body 2. Temperature is T1, temperature is T2. Radiosity is J1, radiosity is J2. Area is A1, area is A2. Shape factor with this with respect to this is F12 and here with respect to this is F21. Yes or no? So you know that total area, total energy leaving 1 and reaching 2 will be J1, A1, F12 minus total heat reaching, leaving 2 and reaching 1 will be what? J2, A2, F21, and if you subtract both you will be getting the net radiation heat transfer. Net radiation heat transfer. Okay. So you know by reciprocity that A1 F12 is equal to A2 F21. From reciprocity you know. So finally what is Q net? Q net is A1 F12 J1 minus J2, or Q net will be J1 minus J2 by 1 by. So if I ask you that what will be the resistance, space resistance from here, why space? Why space? Because it is occurring in the region between the two bodies. So you will say that space resistance is 1 by A1 F12. So finally, my dear friends, suppose one body is here and suppose one body is here. So at the vicinity of the surface, due to this surface there will be surface resistance for this, there will be surface resistance for this, and somewhere in the middle there will be space resistance also. So if I ask you what will be the thermal circuit, what will be the thermal circuit, my dear friends? So what will you tell? This is your EB1, J1, J2 and this is your EB2. Yes or no? So what is net radiation heat transfer, my dear friends? EB1 minus EB2, and whatever resistance are there you can add. So 1 minus epsilon 1 by A1 E1 plus 1 by A1 F12 plus 1 minus epsilon 2 by A2 epsilon 2. Sir, are you getting or not? Are you getting or not? Unit will be watt. Unit will be watt. So let me rewrite. Q net will be between any two bodies, it will be what? Again I have, see, EB1 and EB2, you are missing one thing. Can I write EB1 as sigma T1 to the power 4 and can I write EB2 as sigma T to the power 4 from Stephen's law? Yes or no? So sigma T1 to the power 4 minus sigma T2 to the power 4 divided by 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1 F12 plus 1 minus epsilon 2 by A2 epsilon 2. You can use this for any bodies, right? Are you getting or not? Now my dear friends, see, I will be making one change. I will be making one change. I will be only multiplying with A1 and A1 in the numerator and denominator. Okay. I will be just tweaking this sigma A1 T1 4 minus T2 4 divided by, see here it will be what? 1 minus epsilon 1 by epsilon 1 plus 1 by F12 plus 1 minus epsilon 2 by epsilon 2, and here it is A2 by A1. No. A1 by A2. Sorry. A1 by A2. A1 by A2. Fine. So this is the expression that I am requesting all of you to remember. All of you to remember. And now what I will do? It's very simple. Now I will be just taking, now I will be just considering one, two, I will be taking different cases, like for infinitely plane slab what happens, for infinitely concentric cylinder what happens. All these things I will be doing. Yes or no? But how I reach there, this is important. So infinitely, case 1, infinitely long parallel plates. Suppose two plates are there maintained at T1 and T2. So infinitely long. So what happens? Shape factor will get 1 and area will be A1 equal to A2 is equal to A. These changes I will be making in my previous expression. So it will be what? Sigma A T1 4 minus T2 4 divided by 1 minus epsilon A. Okay, I have considered A. So what changes I am expecting? 1 by epsilon by, let me write in this way, 1 by epsilon 1 minus 1 plus 1 plus 1 minus A1 A2 gets cancelled out. So 1 by epsilon 2 minus 1, 1 by epsilon 2 minus 1. So Q net, and this A I am taking it downward. So it will be what? Sigma T1 4 minus T2 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. And this, my dear friends, I hope everyone remembers. This is the, acha, what will be unit? Unit is for watt per meter square. Watt per meter square. I hope everyone has. Do memorize this formula, but I have just told you how it is coming. And now my dear friends, simple, very simple thing. Here only I am writing case 2 and case 3. What is case 2? Case 2 is infinitely long concentric cylinders. Concentric cylinder. So nothing you have to do. See, this is one cylinder, this is another cylinder, radius is R1 and this radius is R2. So in place of what is A1 by A2? 2 pi R1L by 2 pi R2L, everything gets cancelled out, and R1 by R2. In place of this A1 by A2, you will be putting R1 by R2. Game done, job over. And third, my dear friends, for spheres, for concentric spheres, for spheres what will be A1 by A2? A1 by A2 will be 4 pi r1 square by 4 pi r2 square. So ultimately it will be r1 square by r2 square. You put it in place of a1 by a2, game done. Yes or no? So I told you that you have to just memorize this final expression, and ultimately whatever question comes for anybody, you will be able to do it very easily. Right? So this was the case of your radiation network. This was the case of your radiation network. Everyone has understood this or not? Everyone has understood this? Now what is the concept of radiation shields? What is the concept of radiation shields? See, this radiation shield between infinitely plane slab case we are considering, between infinitely plane slabs we are considering that I have put a radiation shield over here. Okay, this is at T1, this is at T2, obviously T1 is greater than T2. Now suppose the first case when there was no shield, when there was no shield, what was your expression of Q? Your expression was Q was Q by A is equal to sigma yes or no? And now I have put a shield. So tell me one thing, it will induce a surface resistance on the left side, it will induce a surface resistance on the right side, and plus there will be space resistance over here and there will be space resistance over here. So finally if I ask you what will be the thermal circuit, this is one, this is your EB1, so it will be what? Here it will be, let me first draw this circuit and then we will be writing each and every resistance, that is not the problem. I think this should be enough. So first will be what? Surface resistance for this body, so 1 minus epsilon 1 by epsilon 1 A1. Now there will be space resistance between 1 and 3. See, let us consider this is 3, this is 1 and this is 2. So between it will be A1 F13. Is it small or what? Is it small? Okay, let me take it to the next page. No issues. Let me take it to the next page. This is 1, this is 3 and this is 1, this is 3 and this is 2. Okay. So this is EB1. So first will be what? 1 minus epsilon 1 by A1 epsilon 1, then 1 by A1 F13, then the surface resistance from 3 over here, 1 minus epsilon 3 by A3 epsilon 3, then the surface resistance on the right hand side in place of for 2 it will be 1 minus epsilon 3 by A3 epsilon 3, then let us name this resistance 1, resistance 2, resistance 3, resistance 4, resistance 5, resistance 6. So I think I have just inserted one resistance over here, no issues. So 1, 2, 3, 4, 5, 6, fine. So this is what? 1 by A1 F13. This is what? 1 minus epsilon 3 by A3, 1 minus epsilon 3 by A3 epsilon 3. Then this is what? Surface resistance for 3 on the second side, 1 minus epsilon 3 by A3 epsilon 3. This is space resistance for 3 and 2, 1 by A3 F32, and this is for 2, surface resistance for 2, surface resistance for 2, so 1 minus epsilon 2 by A2 epsilon 2. That means I have done nothing. I have done nothing. I have only written all the thermal resistance between 1 and this is your EB2. EB2. And now if someone asks you that what will be Q12, you can write na EB1 minus EB2 divided by this entire total thermal resistance. Total thermal resistance. My dear friends, initially there was 3 resistances. There was 3 resistances on the body if there was no shield, and now there are 6. That means 3 extra resistance have been there due to the shield. Are you getting or not? There are 3 extra resistance. That means 2 surface resistance, and 1 space resistance have been extra incorporated due to the addition of your shield. So all these things you can write it very easily. I am not going into the detail. What I am going into the final expression. The final expression is important. For example, if A1 is equal to A2 is equal to A3 is equal to A, let's say, and you all the shape factor, whatever the shape factor are there, it is equal to 1 because it is parallel. Whatever shape factor is there, it is equal to 1. So what happens, my dear friends? I am writing the final expression. And that is important. In this expression only F12, all these changes I can make, and the final expression is 1 by epsilon 1 plus 1 by epsilon 2, 1 by epsilon 1 plus 1 by epsilon 2 plus 2 by epsilon 3 minus 2. So this is the expression that you have to remember. Now my dear friends, what is the earlier when there was no shield? When there was no shield, what was the Q expression? Sigma T14 minus T24 divided by 1 minus epsilon 1 plus 1 by epsilon 2 minus 1. And this is when case of there is one shield. In case there is one shield. Now see my dear friends, suppose in both the cases I am making epsilon 1, epsilon 2 is equal to epsilon. Let's say I am making these changes. So when there is one shield, it is 1 plus 4 by epsilon minus 2. And here what happens? When there is no shield, it will be T14 minus T24 divided by 2 by epsilon minus 1. So can you conclude something? Can you make an relation between this expression and this expression? If you see closely, my dear friends, it is sigma T14 minus T24 divided by, if you take 2 common, it will be 2 by epsilon minus 1. So this is nothing but this expression only, na? So what happens? Q of between 1 to when there is one shield is equal to 1 by half Q times Q of when there is no shield. This is the expression that we are getting. And similarly for n shields, what happens? Q between 1 to 2 with n shields is equal to 1 by n plus 1 Q when there is no shield. This result is also very important. In place of n, earlier there was 1, so 1 plus 1 2, so that's why it got half. Sir, are you getting this concept? So this is all about, my dear friends, of the radiation shield, and with this the entire discussion on radiation comes to a stop. Right? So I hope You have understood this, and after 1 minute we are going to start with the concept of convection. Fine. So we can start now with the concept, with the chapter of convection. So my dear friends, in this session we have already discussed about conduction, we have already discussed about radiation, and in very detail all the important concepts, all the important formulas we have discussed. And now it is the time for convection, right? My dear friends, the basic law, what is the basic law in convection? The basic law in convection is Newton's law of cooling. What? Newton's law of cooling. Newton's law of cooling. Entire convection, and it is HA T of surface minus T of ambient. Entire convection, this relation I will be using for finding out the heat transfer. Unit of H is what? Watt per meter square Kelvin or degree centigrade, whatever. But still the analysis is not so simple. Why? Because H value is slightly very I can say complicated to find out. It's when I give you the value of H, it's very easy, but when it is not given, then things might get a bit clumsy. Now my dear friends, suppose this is a flat plate which is given. So you know that there will be boundary layer, a fluid is coming, a fluid is flowing from this end with velocity u infinity, temperature T infinity, and so there will be boundary layer formed, that is fine. No slip condition will be there at the surface also, that is also good. But at the same time, let us say the temperature of Ts is more than temperature of infinity, so there will be thermal profile or temperature profile will also be formed over here along with the velocity profile, okay. Now one thing is you have to notice that the temperature of the fluid gets stuck with the surface, so the bottom temperature of the fluid is also same as that of the surface, that is not the issue. So how the heat is going, my dear friends? First the heat is getting conducted from the plate to the immediate surface of the fluid, and then it is getting convected. It means what? It means that Q conduction from the surface is equal to Q convection upwards. So minus K of fluid, now it is with respect to y, so dt by dy at y is equal to 0 is equal to Q convection, that means H T surface minus T infinity. I have considered surface to be at a hotter temperature, so heat to flow from surface to ambient. From here if I try to find the value of H, what it will be? It will be minus Kf dt by dy at y equal to 0 divided by Ts minus T infinity. Are you getting or not? So this is the first important formula or the first important concept that we discuss in convection. My dear friends, you will be thinking that, sir, we have found the value of H, it is so simple, and we put in the formula and we get the value of heat transfer. But my dear friends, this formula is only good or only will come handy when I know the temperature profile. Yes, the temperature profile is a must. So unless I know the temperature profile, I am not able to do anything with this formula. And from now onwards, means I am telling with respect to your whenever you are learning convection in your classroom, your teacher might have told you the journey from here in to finding the temperature profile, that how the temperature profile is coming. So many analysis you have to do. So many, I will be applying continuity equation, I will be applying momentum equation, I will be applying energy equation. On a single fluid element, so many energy analysis I will apply. Like for continuity, I will be doing mass conservation. In case of momentum equation, I will be doing force conservation, momentum conservation, and in case of energy equation, I will be balancing the heat. These three analysis, after doing these three analysis, finally I reach the temperature of the the temperature profile that is developed on a, let's say, flat plate. This is the case of flat plate that I am discussing. All these things you have done in your classroom cases, yes or no? I am just trying to you to recollect all the important concepts. Anyway, I'll be just trying to give you an idea about how all these things are coming. That is not the problem. Anyway, so what are the important numbers that we discuss? Starting from Nusselt number. Starting from Nusselt number, my dear friend, what is Nusselt number? Nusselt number is, let's say, what is Nusselt number? Nusselt number is, let's say, this is a fluid and this is T1 and this is T2. If I ask you what is Q due to conduction, so you will be telling me Ka del T by, let's say this distance is L. And if I ask you what is Q convection from the same fluid, it is H delta T. So Nusselt number is nothing but Q due to convection by Q due to conduction. H delta T divided by K delta T by L, HL by K, HL by K. But here I will write K of fluid. I already told you that in bio number this is K of solid and in here it is K of fluid. So, okay, Nusselt number is HL. Again, if I want to write properly, HLC by K, what is LC? LC is nothing but the characteristic length and K is nothing but K of fluid. Now, my dear friends, what does Nusselt number says? Nusselt number says the enhancement of heat when heat is being transferred by convection in comparison to when heat is transferred by conduction. Just try to imagine heat is being conducted between the fluid layers. So, if the fluid layer is static, let's say just at one place, so fluid heat will be transferred by conduction, layer by layer, layer by layer. It will take a long time, but we don't have that much time. So, when convection will be there, fluid is going to flow and take the heat, there will be a lot enhancement in the heat transfer that will be taking place. So, that enhancement is given by Nusselt number, my dear friends. Okay. Next, what is Prandtl number? What is Prandtl number? Nu by alpha. Nu is signifying momentum diffusivity. Alpha is thermal diffusivity. Nu is what? Mu by rho. Alpha is what? K by rho Cp. K and K gets, rho and rho gets cancelled out. Mu Cp by K. My dear friends, whenever a fluid is flowing on a surface, two types of layer are being formed. One is hydrodynamic boundary layer and another is thermal boundary layer. So, the comparison between the two is given by Prandtl number. Which layer is bigger, which layer is not bigger, which means which layer will be formed to a bigger height than the other layer. All these things will be given by Prandtl number, and for air it is 0.7. So that means you can see that the thermal layer will be more. So all these things, my dear friends, it comes under theoretical part, and I hope you have taken care of that respect. I am only here to tell you about the important formula part. Anyway, this is Prandtl number. Now, so I have told this, I have told Nusselt number, I have told you Prandtl number. Anything more, or shall we go on to anyway? Okay, Reynolds number, this one is missing. Reynolds number, inertia forces by viscous forces, final expression is rho v x by mu, rho v x by mu, inertia forces by viscous forces. So this you have already studied. X I have considered in a particular distance. So for L you can write L, that is not the issues, rho v x by or rho v L by mu. Okay, make it L only, that is not the problem. So this, all these numbers, and later on I will be talking about Grashoff's number and all those things. Okay, Nusselt number is HL by K. Fine. Now my dear friends, I was talking about how the temperature profile is being developed. Now let me give you a quick recap. That how the temperature profile is being obtained. Sir, why do you need temperature profile? You may ask me that, sir, why do we need temperature profile? Because that temperature profile I will be putting it over here and I will be getting the value of H. Sir, what if we get the value of H? I will be able to get the amount of heat transfer. Sir, how? I know Q is equal to HA delta T. Done. Done. That's it. Getting or not, sir? So what is continuity equation? Continuity equation is del U by del X plus del V by del Y is equal to 0. This is obtained from mass conservation. This is obtained from mass conservation. See, these things you need not remember. It's not required to remember over here. In heat transfer, in fluid you may remember. Over here it is not required, but still I am trying to give you that how the temperature profile is obtained. Now what is momentum equation? Momentum equation is U del du by dx plus V du by dy is equal to nu d2u by dy square, and this is nothing but your momentum equation, force conservation. And finally, if I apply the energy conservation or energy equation, how do I obtain energy equation? If I balance the energy, and that result is, my dear friends, U del dt by dx plus, I should write del because it is now varying with x and y, V del t by del y is equal to alpha del 2t by del y square, and this is, my dear friends, your energy equation. Now see, what is the logic? I'll quickly tell you what is the logic. The logic is, from these two equations I obtain u and v. See, this is a differential equation, this is a differential equation. From here I obtain the value of u and v. This u and v I put it over here and I get the value of temperature profile. In short, this is the logic. From the first two equations, uv put over here, you get the value of temperature profile. That's it. This is the the chronology that we are talking about. Okay. So for example, if you solve this, if you solve the first two, what you will get? A cubic profile u by u infinity is equal to 3 by 2 y by delta minus half y by delta cube. Yes or no? This is the relation that we get. And similarly, what is the temperature profile that we get? What is the temperature profile that we get? Same, 3 by 2 y by, in place of delta I will be writing thermal thickness, thermal boundary layer thickness, minus half y by delta T cube. So this is the, see, this is how we have reached the thermal profile, the thermal boundary layer profile. And once we have got this, what we can do, I can very easily find out, see, T minus T infinity, T minus Ts is what? T infinity minus Ts my dear friends, if I differentiate it over here, dt by dy, if I find dt by dy at y equal to 0, so what will happen? This thing T infinity minus Ts, if I differentiate, I'll be, see, if you differentiate and put y equal to 0, this term will be gone. So it will be 3 by 2 delta T. This will be left, yes or no? This will be left. 3 by 2 delta T, okay. So what will be dt by dy at y equal to 0, 3 Ts minus T infinity by 2 delta T, yes or no? Okay, T infinity minus Ts, T infinity minus Ts, that is not the problem. T infinity minus Ts. And now my dear friends, why I am finding all these things? Because you know that in the first page we have already discussed minus k dt by dy at y equal to 0 divided by Ts minus T infinity, yes or no, from the first page. So if you substitute this, my dear friends, what we are getting? And Ts minus T infinity. So finally what we are getting? 3k by 2 delta T, yes or no? Finally we are arriving at 3k by 2 delta T. So what is H? H is 3k by 2 delta T. So this is just an example of obtaining H. Sir, are you getting? This is just an example of obtaining H from a given thermal profile. Let's say your thermal profile is cubic. This is delta T, that means H is equal to 3k by 2 delta T, thermal boundary layer thickness. My dear friends, see, I am telling you one very good thing. We know that delta by delta T, I'll tell you one very good thing. Delta T by delta is equal to 1 by 1.028 Prandtl number to the power 1 by 3. This is one expression connecting your thermal and your hydrodynamic thickness. Okay. Again, you know what is delta hydrodynamic boundary layer thickness. What is delta T? Thermal boundary layer thickness. Now you know that there is a relation of hydrodynamic boundary layer thickness 5.64 x by root over Reynolds number x. Okay. 5.64 x by, in place of Reynolds number you will be putting what? Rho u x by mu, rho by x by mu, and ultimately what we are getting, root x divided by, see, root x goes up and here it is what? Rho u by mu, root x gets cancelled. So I am interested that what I am getting there is delta is proportional to x to the power 1 by 2. This is the important observation from here. Sir, are you getting or not? and if delta varies, square root of x, so delta t will also vary. Why? Because this thing is nothing but your constant. The right side is constant, so whatever way delta will vary, delta t will also vary. So delta t is also varying with respect to half of x, square root of x. Sir, why are we telling all these things? Because we know here that h, how h is varying? H is inversely proportional to delta t. From here what I am writing? H is inversely proportional to delta t, and delta t is varying x to the power 1 by 2. So how will h vary? H will vary. How will h vary? How will h vary? H will vary as x to the power minus half. So this is, this I have just told you how h is going to vary with respect to your distance. That means whenever you go forward, your h will come down. Whenever you go forward, your h will come down in this square root fashion. So all these are, you can definitely expect all these questions for 1 marks. That's why I am telling you all these things. And without wasting any time, my dear friends, flat plate, I just wanted to give you some insight about how the formulas are being developed. Anyway, flat plate, laminar flow, my dear friends, flat plate, laminar flow, local Nusselt number. This is the expression that you have to memorize. This is the expression that you have to memorize. This is the expression that you have to memorize for a laminar boundary layer, laminar boundary layer. Okay. Now you also know that if I have to find out, see, this is the local Nusselt number, local h, all these things, it's a, for any distance x. But if I have to find out, the average, so the derivation I can do it, but it is of no use. So for the average heat transfer coefficient, see, this is the heat transfer coefficient at any distance x, but for average you know that it is going to get doubled, REL 1 by 2 and Prandtl number 1 by 3. How it is coming? I can do it very easily, but that is not required, and ultimately you have to keep these equations in mind. Always remember, this is for a laminar flow, flat plate, laminar flow. Okay. So are you getting these things, my dear friends? Are you getting all these things? Okay. So all these things are fine, my dear friends, and now one important concept comes, Reynolds-Colburn analogy. Reynolds-Colburn analogy. See, Reynolds analogy, it is used for connecting FM and HT. FM and HT, it's a bridge between FM and HT. See, I'll tell you in very short. What is wall shear stress? In FM you have studied mu du by dy at y equal to 0. Also you have studied, tau for wall is half CFX rho u infinity square, yes or no? This also expression you have studied. So let's say this is 1 and let's say this is 2. So from 1 and 2 I can write CFX by 2 minus half. Okay, from 1 and 2. Now my dear friends, in HT what you have studied, see this is from FM, this is from FM, and from HT what we have studied, NUX is equal to HX yes or no? So suppose NUX divided by REX into Prandtl number, if I divided both the sides, I will be getting 332 1 by half and Prandtl number minus 2 by 3. This number is called Stanton number. So local Stanton number is equal to 0.332 Reynolds x minus half Prandtl minus 2 by 3. So take Prandtl over here. So by Prandtl number 2 by 3 is equal to 0.332 Reynolds x to the power minus half. So check this thing and this thing is same na, this thing and this thing is same na, so I can equate na both the things, yes or no? Sorry, it is minus 2 by 3 when it comes, so it will go up, so don't worry, it will go up, so it will be Stanton number, local Stanton number, Prandtl number to the power 2 by 3 is equal to CFX by 2. Sir, are you getting or not? And this is how we can connect the FM and your HT. My dear friends, something more on what is local Stanton number. So what is NUX? HX into X by K. What is Reynolds number? Rho UX by mu, and what is Prandtl number? Mu Cp by K. So mu gets cancelled, K and K gets cancelled, X and X gets cancelled. So what is left? Hx by rho u Cp, Hx by rho u Cp. So see, in Stanton number there is H and this is skin friction coefficient. This is what? C is your skin friction coefficient. So this is from FM, this is from HT. So FM and HT, once you know skin friction coefficient, you can very easily able to find the value of Hx, and from here you can able to calculate the value of the total heat transfer by using the Newton's law of cooling equation, HA delta T. Okay, so I hope you are getting my difference. So this was the first part of your, this was the first part of your convection. Just a minute. Now my dear friends, we are going with the second part of forced. This was all about forced convection, yes or no? This was all about forced convection. And let us go into the second part of forced convection, and that is the internal flow. That was external flow, and now I have to deal with internal flow. That means flow through pipes. What happens in flow through pipes? What happens in flow through pipes? Suppose this is a pipe. From here fluid is entering, so it will have a, let's say, a velocity, mean velocity of mean temperature of TMI, and from here you are giving some heat. So this fluid, as it flows, it will get heated, and when it goes out, let's say its temperature is increased to TMO. We are talking about the mean temperature. My dear friends, why I am talking about the mean temperature? Because from this wall to the center, the temperature is going to vary. We have studied in FM also that from the wall to the center, the velocity varies in a parabolic fashion. Same in case of temperature also, it is going to vary. The temperature of fluid will be higher over here and lesser at the center. But we avoid this variation and we use a average velocity concept in case of flow through pipes. That is why in calculation of discharge we use the concept of average velocity, yes or no? Here also the temperature is varying from wall to the center, but we are ignoring that and we are considering the concept of average mean temperature of the fluid. That is why over here I have considered TMI, mean temperature. See, at the beginning it will be mean only, at the outside it will be mean only, but in the when it is flowing, there the temperature will vary, and then I have to consider the concept of mean temperature. Okay. So just keep this in your mind that whenever I am telling you the temperature of fluid in pipe or outside pipe, I am talking about the mean temperature. Anyway, here it is the surface temperature. So from the surface heat will be transferred to the fluid, and then only the heat transfer will take place, yes or no? So what is the scope of heat transfer over here? The scope is that when the fluid is flowing from the surface heat, the surface heat is at a higher temperature, from there the heat is getting transferred to the fluid is getting heated and it is coming out at a higher temperature. I hope you have got this concept. So if I ask you what is Q, so Q will be HA, and let's at any section if I consider Ts minus Tm, the surface temperature minus mean temperature. Q by A I can consider as heat flux Ts minus Tm. Ts minus Tm. So Q by A is heat flux Th minus Tm. So what I can write? Q by H is equal to Ts minus Tm, or Tm is equal to Ts minus Q by H. My dear friends, when a fluid is flowing through pipe, one thing I can say is this thing is always varying. The mean temperature of the fluid is always changing. So H is constant. H for a fully developed flow is always constant. So Ts and Q, both the things cannot be constant at the same time. Very important. Ts and Q, that means surface temperature and Q, will not be constant at the same time. Either Q will be constant, so Ts will be varying, or Ts will be constant, so Q will be varying. Both will not be constant at the same time. Very important things. That is why we study two cases over here. The case one is when heat flux is constant. And case 2 is when surface is constant, and my purpose is still the same. My purpose is still the same, that how the temperature is going to vary and in both the cases, and heat transfer obviously. So if I consider the heat flux is constant case, and let us say this is the pipe, so this is TMI and this is TM outside or outlet. Let us say I have wrapped this entire cylinder in with a wire, so that means the heat H is constant. So what you have to do, if you have to analyze this case, you have to consider an element at a particular distance x. So, and let us say the temperature over here is Tm, for the fluid it is Tm. So what happens, till x distance how much heat has been supplied, my dear friends? How much heat is being supplied? Q into the area, that is diameter is d, so pi dx, Q into pi dx is equal to H, and till this x distance it is Tm minus Tmi. Getting or not? Q into pi dx is equal to getting or not? Q into pi dx into is equal to, not H actually, it is I should write not H, it is MCP Tm minus Tmi, MCP Tm minus Tmi. So Q into pi dx divided by MCP plus Tmi is equal to Tm. So this is how the temperature is being varying. So if I ask you how the mean temperature of the fluid is changing, so you let me write the expression once again. Tm is equal to Tmi plus Q into pi dx divided by m dot Cp. This is the expression, my dear friends. And if I ask you how it is varying, so see, this is constant, m is constant, Cp constant, Q is constant, pi d, everything is constant. So Tm is varying. So Tm is varying linearly. How the variation is there? It is varying linearly. Now, my dear friends, from the first page, we know this thing. Q by H equal to Ts minus Tm. Ts minus Tm is equal to Q by H. Your Q is constant, H is constant, so this difference must be constant, and this is varying linearly, so surface temperature will also vary linearly. Yes or no? Your surface temperature will also vary linearly. So if I have to make a plot, it will be what? This is for T mean of with x the temperature, and this is of Ts, this is of Tm. So variation will be linearly. Okay. So I hope you have understood this point. Next is what? Case 2 is what? Case 2 is constant surface temperature. My dear friends, constant surface temperature, again I have to take an element, I have to make the analysis that how much heat is being how much heat is being acquired by the fluid for an incremental change in temperature. Sufficient to know that the final expression will be somewhere around, I am writing the final expression, my dear friends. This is what is important. sufficient to know that the variation will be logarithmic in nature or exponential in nature. Previously it was varying linearly. Second, in the second case, whenever there is a constant surface temperature, the temperature of the fluid will vary in what fashion? Exponentially or logarithmically, whatever you want to say, because both are inverse of each other, that's why. So these are the two cases, my dear friends, and always remember, questions do come from this section. Questions do come from this section. Suppose if I ask you that how much is the total, suppose this is the fluid, this is the pipe, and this is TMI and this is TMO. How much is the total fluid acquired by, how much is the total heat acquired by the fluid? If I ask you this, you will be saying, sir, MC TMO minus TMI. And obviously some flux will be given into pi d L. So always remember such equations in the back of your mind. This is flux into total area is equal to total heat rise in temperature. So such questions do regularly are coming in GATE. So always have, just take care of this concept. I hope I have told everything regarding this. Yes. Now my dear friends, this was all about your forced convection. External flow, internal flow also done, external flow also done. And now let me quickly tell you the concept of free convection. My dear friends, in free convection, you know that buoyancy force will come into picture. In FM, whatever buoyancy force you have studied, there it is due to pressure difference. Here it is due to density difference. How? I am just telling you. Suppose this is some object kept, a food kept on your table. It is very hot. So air will come to it. It will acquire some heat. It will get light and it will go up. Yes or no? It will go up. Its density will come down. Once its temperature increases, its density will go down and it will go up. Similarly, more air will come. It will acquire heat, go up. So if air I am considering, air I can consider what? Ideal gas. So I can write what? PV is equal to MRT, ideal gas equation, yes or no? So P is equal to mass by volume rho RT, yes or no? P is constant, atmosphere, R characteristic gas constant. So rho into T is equal to constant. Yes or no? So when rho into T is constant, it means what? It means when temperature of the air is increasing, the density is coming down. That's why when it is getting lighter, air moves up. So this is the concept which we can apply in case of free convection. Fine. One more thing, one more concept is there, volume expansivity. The second concept which comes into picture is volume expansivity. What is volume expansivity? Beta is equal to variation of V with temperature at constant pressure with respect to initial volume. This is the concept of volume expansivity. What is volume expansivity? The change in volume with respect to temperature whenever the pressure is constant. For example, I am considering ideal gas air. So PV equal to MRT. So what we can write? V is equal to M by P RT. So what is del dV by dt? mR by P. mR by P. So and mR by P from the first equation, mR by P is equal to V by T. Yes or no? So this is nothing but V by T. So if you put it over here, it will be 1 by V into V by T, and ultimately it is 1 by T. So this is what beta equal to 1 by T for ideal gas. For ideal gas, beta is equal to 1 by T, and just remember beta is equal to 1 by T, and just remember that this T is in Kelvin. This T is in Kelvin. This T is in Kelvin. It is the mean temperature of the surface and the external ambient. Okay. T is equal to T mean plus T infinity by, okay, volume expansivity. This is beta. Fine. Acha, one more thing. My dear friends, what is beta? Beta is 1 by volume dV by dt at pressure equal to constant. See, mass we are taking as constant, so rho v is equal to constant. If you differentiate both the things, differentiate both the sides, rho into dV plus v into d rho is equal to differentiation constant 0. So rho dV is equal to minus v d rho. So dV by v is equal to minus d rho by rho. This also is very much important. So what happens if I have to write beta in terms of density, I have to write 1 by rho d rho by dt at pressure equal to constant. Okay. So beta is equal to minus 1 by rho d rho by dt. From here, if I have to write d rho, I will be writing minus beta rho dt. Now where I will be writing, you will be knowing in some short time. Okay. Sirs, are you getting? Now my dear friends, I have already told you that what over here, see, free convection takes place due to density difference. Okay. In fluid it was due to pressure difference, and over here it is due to density difference. So suppose this is a hot surface kept. Suppose this is a hot surface kept. There is air over here at a very long distance, at a very far, its temperature is T infinity. When you bring this air over here, its temperature, it will get heated and it will try to go up. Now what is the force responsible for taking it upwards? Buoyancy force. But at the same time, you know that its inertia force will try to pull it down. So buoyancy force, if I try to analyze this air, buoyancy force will pull it up, inertia force will pull it down, and when it goes up, when it is going up, there will be viscosity also, and that viscosity will create friction, and due to that friction it will try to pull it down. So all in all, if I have to say, this element, this air element, buoyancy is taking it upward, but inertia and viscous force are pulling it downward, buoyancy is taking it upward. All in all, in free convection there are three important forces that comes into picture: buoyancy force, viscous force and inertia force. And using these three forces, we have to construct one dimensionless number. If I talk about what is buoyancy force, it is nothing but rho g v. See, why I have written delta rho? Because due to change in density only buoyancy forces come into action. Now in place of v, see this is delta rho, and here only I have told you that d rho is what? Minus beta b rho beta delta dt minus rho. See, minus will be taken care of, don't worry about that. Rho beta delta t. This is g, and this volume I can write L cube, the major characteristic dimension. What is inertia force? What is inertia force? Inertia force will be rho v square L square, rho v square L square. And what is viscous force? Viscous force is mu VL, mu VL. Yes or no? So what is Grashof number? It's time to create one dimensionless number using the 3. So FB into Fi by F viscous force whole square. FB into Fi by F viscous force whole square. So what is FB? FB is rho beta delta T G L cube. What is inertia force? Rho V square L square. And what is mu? Mu square V square L square. So V square L square, V square L square is gone. This rho and rho will become rho square beta delta T G L cube divided by mu square. So mu square by rho square is nu square. So ultimately what is becoming? G beta delta T LC cube by nu square. So what is Grashof number? G beta delta T LC cube by nu square. This is the characteristic, this is the number that is used in free convection, my dear friends. Now why I have written LC? LC means characteristic dimension. Here also the concept of characteristic dimension comes into picture. What is characteristic dimension? The dimension where the predominant direction in which convection is taking place, free convection is taking place. Getting or not? Getting or not? So my dear friend, now I am going to write some empirical relationships and you have to just know that over here, see there in case of forced convection, Nusselt number was a function of Reynolds number and Prandtl number. Here in case of Reynolds, it will be replaced by Grashof number. Simple. So Nu is equal to C times Grashofs into Prandtl to the power n, where n is equal to 1 by 2 in case of laminar and n is equal to 1 by 3 in case of turbulent. And all these things, my dear friends, you know that when Grashof number into Prandtl number is less than 10 to the power 9, the flow is laminar, and when it is greater than 10 to the power 9, the flow is turbulent. So all these are empirical relations, my dear friends, and from here you will be very easily able to find out. So what is the concept? The concept is, first we will be finding beta, then we will be finding the beta, G delta T LC cube, all these things, Grashof number, after Grashof number Prandtl number mu Cp by K, you put it over here, C and N value they will be giving you, you find Nusselt number, and when you find Nusselt number you find H, and when you find H you find heat transfer by using HA delta T. Fine. One more thing, my dear friends, one more thing. In case of forced convection, I told you that in a fully developed flow, the value of H is constant. Okay. All those equations was for laminar, and once you enter into turbulent, once the flow gets turbulent, we use Ditter-Bilter equation for finding the Nu. Yes or no? And what is Ditter-Bilter equation? For flow for turbulent, although they will give you, see in many examinations in the GATE only they have given you this expression, still I am writing it just for you to be sure. For turbulent we use Ditter-Bilter equation, and that is nothing but Nu is equal to Hd by K. Why I am writing D? Because for flow through pipe the characteristic length is diameter, is equal to 0.023 Reynolds number to the power 0.8 and Prandtl number to the power n. So n is equal to 0.4 when fluid is heated, and this is when cooling, when n is equal to 0.3 for cooling. So this is what Ditter-Bilter equation for internal flow, this is flow through pipe. Flow through pipe. Okay. So I hope that I have discussed most of the important concepts. I have discussed all the important concepts when it comes to convection. And now, my dear friends, after 1 minute, I am going to finally do the uh, heat exchangers, and after that we will be closing the session. So after a break of 1 minute, we will be starting with heat exchangers. Fine, the final chapter. So, welcome everyone. My dear friends, this is a session of heat transfer formula revision session. From 1 p.m. we have started this session and we have completed all the big three important chapters which are there: conduction, convection, radiation. And finally, we are going to discuss about heat exchangers and we will end this session, right? So, let us know about heat exchangers. My dear friends, heat exchangers is a steady state adiabatic device. Adiabatic means Q is equal to 0. Fine. Steady state, that means you can apply a steady flow energy equation. A steady flow energy equation you can apply in this Q equal to 0. What happens in heat exchangers? There is a device. From here hot fluid is flowing, initial temperature THI, THO. Cold fluid is also flowing, TCI and TCO. So, some fluid is given by heat, hot to cold. And finally, my dear friends, we can apply this equation, which is heat lost by hot fluid is equal to heat gained by cold fluid. So, it is what MCH CPH THI minus THO is equal to M dot C CPC TCO minus TCI. Always remember this thing, this equation will be very handy. Now, the concept of overall heat transfer coefficient. Overall heat transfer coefficient. What is the concept, my dear friends? Let me tell you. Suppose in this cylindrical device, a fluid is flowing in the inner cylinder and some outer fluid is flowing over the cylinder, and this is the, from here heat is getting transferred having material K. So, if I ask you what is the total thermal resistance? What is the total thermal resistance? So, you will be telling me that, sir, it will be 1 by HIAI plus ln R2 by R1. Okay, this is R1 and this is R2 by 2 pi KL, the length of the cylinder is L, plus 1 by HO and AO. My dear friends, what is the concept of overall heat transfer coefficient? The concept is that if I remove all the things, and if there is only, this is the inner temperature T1 and this is the outer temperature. If I remove all the fluid, all the cylinder, and if I just replace, if I want to find just one value of the heat transfer coefficient using which the entire heat will be transferred, so that is called heat transfer coefficient. And overall heat transfer coefficient UA delta T, this is the concept. That means removing all the things, delta keeping same, what is that overall heat transfer coefficient by which we can carry the same amount of heat. So, 1 by UA is equal to delta T by Q. Yes or no? I can write what? I can write what? Delta T is equal to Q into the thermal resistance, and in place of this thermal resistance only I can write what? Delta T by entire thing. Delta T is equal to Q into 1 by UA. Delta T is equal to Q into 1 by UA. Now just see this thing, delta T Q RTH 1 by UA. So I can equate 1 by UA and this RTH. Yes or no? And finally, my dear friends, if I put AI is equal to A naught is equal to A, suppose this is happening. Why it is happening? Because generally the heat, the material is very thin, and if it will not be thin, it will offer much resistance, higher resistance. Yes or no? So if it is, it means I can write Ri is equal to R naught when both the areas are same, and when Ri equal to R naught or R2 equal to R1, it ln1 it will get cancelled out. Ln1 it is value 0, and AI, A naught, everything is 0. So finally, my dear friends, I am arriving at this situation. So in case of heat exchangers, what is your overall heat transfer coefficient? The overall heat transfer coefficient is 1 by Hi plus 1 by H1 plus 1 by H naught. If they give you fouling factor, so simply add the fouling factor also and then find the overall heat transfer coefficient. But most of the times, if I speak with respect to problems, most of the times heat transfer coefficient value is already given to you. Okay, so you need not worry. And finally, what you can do, UA delta T. Now tell me one thing, see, Q value I can very easily find out by seeing that which fluid is getting heated or getting cooled by what temperature, mCp dt. U value I am saying that they will generally give, see, fluids are given, so Hi H naught is fine, so I can calculate U. A value I need to find out. See, my objective is to find the size of the heat exchanger, so A value I need to find out. What about delta T? What about delta T? Because the temperature difference between hotter fluid and colder fluid, it is varying with respect to distance. Here the change is different, here the change is different, here the change is different. So whenever I am going along the heat exchanger, this delta T is varying. So when something is varying, how can I take a particular value of delta T? So for that purpose only, I have to find one average temperature, and that average temperature is nothing but your LMTD, logarithmic mean temperature difference. So my dear friends, this is in case of a parallel THI, THO, TCI, TCO. So this is nothing but delta T1, this is nothing but delta T2. I hope you all know these concepts. So what is LMTD? LMTD is delta T1 minus delta T2 by ln of delta T1 by delta T2. What is delta T1? The delta T1 value is THI minus TCI. What is delta T2? The delta T2 value is THO minus TCO. You can very easily, means temperature difference at the exit, delta T2, temperature difference at the inlet, delta T1. You get LMTD, you put, so after finding LMTD, you put over here A, Q you know, U you know, you find the value of A, the size of the heat exchanger, you are very easily able to find out. My dear friends, same, this was for what? This was for what? This was for parallel. Now counter flow heat exchanger. What is counter flow heat exchanger? THI, THO, TCI, TCO. Now this delta T1 is what? THI minus TCO, And what is delta T2? Delta T2 is THO minus TCI. My dear friends, here we get the same value of LMTD, which is delta T1 minus delta T2 by ln of delta T1 minus delta T2. Same value of LMTD we get, but the definition is different. Here delta T1 is THI minus TC naught, and here delta T2 is different. There delta T1, delta T2 was different. I hope you know all these things. Special cases. Case number 1, when one of the fluid is undergoing phase change. One of the fluid is undergoing phase change. One of the fluid is undergoing phase change. In that case, whether it is counter, whether it is parallel, the value of LMTD in case of parallel or in case of counter flow remains to be same. So suppose, what is the difference? I will tell you with respect to questions. Suppose they have given you a question and they have only mentioned that a fluid is undergoing phase change. Now you will be thinking that, sir, what to apply, whether to apply a parallel, whether to consider parallel, or whether to consider counter flow, because you know the definitions are different. But when it is phase change, you consider anything parallel or counter, you will get the same value of LMTD. Let us say you have assumed that the heat exchanger is parallel, you have found out the value of delta T, and you have found out the value of whatever they are asking. Second, when heat capacities are same in counter flow heat exchanger. My dear friends, when heat capacities are same in counter flow heat exchangers. Okay. See, MHCPH THI minus THO is equal to, we know this thing, M dot C CPC TCO minus TCI. They are saying the heat capacities are same, so I have cancelled. So I can arrange this TCI minus TCO is equal to THO minus TCI. And if you just observe, this is nothing but your delta T1 and delta T2 in case of counter flow heat exchanger. So what happens to LMTD? In LMTD, delta T1 minus delta T2 by ln delta T1. See, if you put all these things, it will be 0 by 0. 0 by 0, and when you apply L'Hopital's rule, the final LMTD will be either delta T1 or delta T2, and it will be same only, delta T1 or delta T2. And my dear friends, such type of heat exchangers are called balanced heat exchangers. Balanced heat exchangers. Getting or not? Fine. Now my dear friends, what is the next topic? The next topic is effectiveness of heat exchanger. Effectiveness of heat exchangers. What is effectiveness of heat exchanger? Q of actual divided by Q of maximum. Q of actual divided by Q of max possible. My dear friends, tell me one thing. There are two fluids, one with a lower heat capacity rate, one with a higher heat capacity rate. Which fluid has the potential to undergo maximum temperature change? The one with the lower heat capacity rate. Getting or not? So if there are 4 temperature THI, THO TCI, TCO, what will be Qmax? Qmax will be m dot Cp, whose it is lower, and what is the maximum temperature? Thi minus Tci. Getting or not? This is the maximum temperature. This is the maximum temperature change, which is the maximum overall heat transfer possible in case of two fluid. Now, my dear friend, tell me one thing. If hotter fluid is having lower heat capacity, so what will happen? You will put the Q actual for the hotter fluid. So effectiveness will be what? See, if you put mCp for hot, and let's say mCp, lower is of hot, so Thi minus Tci. So these two gets cancelled out and we are left with Thi minus Th naught by Thi minus Tci. Similarly, if colder fluid is having lower heat capacity, so effectiveness will be what? mCp for cold, Tc out minus Tc in, divided by mCp cold, Thi minus Tci. So finally, when these two gets cancelled, we are Tc naught minus Tci divided by Thi minus Tc. This is the formula for heat exchanger effectiveness when this is the thing. What is NTU? Number of transfer units is UA by m dot Cp of the lower fluid. U is what? Overall heat transfer coefficient. A is area of the heat exchanger. M dot Cp of the lower fluid. It is signifying the size of the heat exchanger. Okay. What is heat capacity ratio? Heat capacity ratio is m dot Cp of the lower by m dot Cp of the higher fluid. Obviously, its value is between 0 to 1. Okay. Okay. So what happens that for any heat exchanger, effectiveness is a function of C comma NTU. For any heat exchanger, effectiveness is a function of heat capacity ratio and NTU. Getting or not? And finally, my dear friends, for parallel, now I will say you to remember this formula, although it's a big formula, but I want you to remember this formula. For parallel flow heat exchanger, effectiveness is 1 minus e raised to minus 1 plus C NTU divided by 1 plus C, and for counter flow, it is 1 minus e raised to minus 1 minus C NTU divided by 1 minus C e raised to minus 1 minus C NTU. Okay. I will suggest you to remember, but it's up to you, because you know that in examination the questions that comes will be maximum from these special cases. What special cases? I am going to write after some time, in just 1-2 minutes. But if you remember this, it will be good only. So I am leaving up to you at what do you want to do. Anyway, special cases, my dear friend, is special cases. Case 1 is one of the fluid is undergoing phase change. So in this case, my dear friends, effectiveness of parallel will be equal to effectiveness of counter flow will be equal to 1 minus e raised to minus NTU. And what is case 2? Case 2 is the heat capacity ratio, the capacity rate ratio, that is C, its value is 1. So in this case, effectiveness for parallel becomes 1 minus e raised to minus 2 NTU by 2, and in case of E of counter, it is NTU by 1 plus NTU by 1 plus NTU. So see, when in case of LMTD also, whenever there was a phase change, there we saw the LMTD of parallel and counter was same. Here also, whenever there is a phase change, effectiveness of parallel and counter is coming out to be same, which is 1 minus e to the power minus NTU. Fine, no issues. And in case of capacity rate ratio, parallel and counter is having. So what I am trying to say is that yes, question mainly have come from the special cases only. If your luck is good, you are going to get question from special cases only, but still in this time of uncertainty, I would not suggest you not leave this formula. So I will suggest you to remember this formula completely. That being said, it's up to you. Final decision lies in your hand. You are responsible for your decision. Anyway, so my dear friends, see, LMTD method, we generally find the size of the heat exchanger. The ultimate output is size finding. And in case of effectiveness NTU method, we generally find one of the exit temperatures. In case of effectiveness method, you will be given the area, you will be given the heat, you will be given all the things, you have to find one of the exit temperatures. Fine. So all these things are there, my dear friends, and with this I have finally completed your entire heat transfer formula revision, concept revision. I started with conduction, then we discussed radiation, then we discussed convection, and finally we are discussing heat exchanger. This complete 3.5 hours, 4 hours of time we have utilized in revising the concepts. And I hope that for people who have watched this, I am sure that you will be benefited and you will be feeling confident. My dear friends, GATE is here and I wish you all the best. Please be relaxed, please be calm and have faith on your knowledge, have faith on your abilities, and I hope that you do well. My dear friends, we will be meeting after the examination for sure, and I will wish you all the very best for your examination, which is on the next Saturday, Sunday. So till then, stay tuned my dear friends, and all the very best. Thank you. Take care.